Good afternoon and welcome. My name is Mark Richardson with Vibrant Technology, and I welcome you to another MEscope ODS Videos webinar. I'm joined by Dan Ambray from Full Spectrum Diagnostics, and today's webinar is titled Gears, Couplings and Isolators. And before we get going, just a couple items here. All attendees will remain on mute for the extent of the webinar. If you have questions, feel free to type your questions in the questions box there in the GoToWebinar panel on the right side of your screen, and we'll try and get as many questions as we can answered at the tail end of the webinar. Incidentally, this webinar is being recorded, so you will get a link to the entire webinar probably tomorrow or the day after it's done processing. With that, let me hand things over to Dan and we will get started.
Good afternoon, everybody. This is Dan Ambray. This is probably the 12th, I think, webinar we've done on MEscope ODS videos. And today's going to be something really different. And I know I say that every time because everybody's learning new stuff from the video analysis, but this webinar is going to involve things that you don't normally see, and I'm in that group, and there's a lot of things that I picked up over the last couple months on different types of machinery, especially gearing and couplings. And what you're seeing right on the screen here is a torque platform in the middle, and two couplings, two Shim couplings, one driven by the motor and one driving the gearbox or the compressor on the other side. Normally you'd have guards on this and you wouldn't be able to see, and thus you couldn't do your video. And in this case, the whole setup was designed for me to come in there and look at the couplings. This application, they have some of the compressors that you see on the right here that are out in the field, and they started failing couplings. And so they asked me to come in and take a look at how their test stand is behaving. So this is nice in that it's a nice clean environment. There's a lot of control that we can do. We can do things that can't be done in the field. And it was an interesting job. MEscope ODS videos, if you're new to it, it's high-speed video vibration analysis. The clip is processed with something called an optical flow algorithm. It enhances all the little displacements and rescales the amplitudes, and now we can see what moments ago we couldn't see, and we can create a video animation of that, and we can pick out problems that we've never seen before. And that's good and bad. As I mentioned, I've seen things in the last week I've never seen before, and you know, I try to make sense out of the motion. Okay. And everybody runs into that, and I don't want to scare you away or anything, but it's still a learning experience, very interesting stuff. And it's been a big part of my business lately. Let's step through this. Where is it? My screen's locked for some reason. Sorry about that. Let's see if it breaks free here. There we go. Okay, this is that same system we just looked at. Okay.
Oh, we're not there yet, Dan. I don't see anything.
You don't see anything?
No.
Oh, great. Okay.
Waiting. It says waiting to view Dan's screen.
I
I don't know if you have to hit go or somewhere.
No, I don't think so.
There we go. Now we see it.
Okay.
That's it. That's it.
There's some show screen button. I should have known
there
that.
You go.
All right.
There we go. Yep. Now we're seeing.
You saw this page though, right?
Yeah, we got that page. Yep.
Oh, okay.
Yeah. There you go.
What this is ODS video, and I pointed right at the center of the system on the torque platform, and I shot the entire wide view. So I got both couplings, the end of the motor, the end of the compressor, and the torque stand. And I put on the orbit plot so I could see the motion. And you can see it. It looks like it's kind of galloping on either side of the torque stand there. But the orbits gives you a good idea of what the direction of the motion is. So if in the torque direction or the twist direction would be vertical, in the axial direction, that would be the thrust related problems. And it looks like a lot of these orbits are longer in the axial direction than in the vertical direction. So, and it makes sense. And it looks like what we're seeing. Now I'm going to do, since it's a variable frequency drive, I'm going to show you several different frequencies that we stepped through. So we did the step sweep from 100% speed down to 45% speed. So we could see if there was some kind of torsional problem with the system. So here was the 100% speed. It's 60 Hertz, I think, for 3580 RPM. This is 3225, so this is 90% speed, and you can still see the orbits are a little smaller in size, but they're still in the axial direction for the most part. There's a little more axial than vertical. This is at 2865 or 80% speed, and it looks like a sweet spot. We've lost a lot of the amplitude in the orbit. There's still some thrusting motion that you can see in that direction, but this is, as it turns out, one of the characteristics of the Shim pack coupling is that it dissipates energy that way, and it keeps the alignment, tolerates a lot of offset misalignment, but it also will have to move a little bit in the Shim packs to be able to do that. So we're at 80% speed. This is down to 65. And again, you can see all the other things going on. This is what caught our attention. Actually, the speed sensor caught our attention first, but the platform with the torque meter on it is moving. And after processing a few of these things, we came to the conclusion that our test stand didn't look like real life at all. And what's happening in the field is they have a no torque stand, obviously. They have a single coupling, and actually they have a different size coupling. That's another issue that we'll get into. So we thought, hey, let's modify the test bed, take out the torque stand, move the motor over, and just have one coupling. And now we have a system that simulates a little better what's happening in the field. Because the point of all this wasn't to see this, hold on. It wasn't to see this wobbling system. It was to judge a torsional response. And we didn't quite know what we wanted to do initially, and it was a work in progress. But part of that was getting the test setup correct. Oop. This is one of the Shim pack couplings that I'm talking about. This little diagram came from the internet in sizing and so forth, but the disc pack is on either side of the spool piece in the middle. So this is my compressor side hub. I have the Shim pack in there. This is the spool piece that's on the inside that's kind of a U-shape, high diameter on the ends and lower in the middle. The Shim pack itself is a bunch of thin plates, and it's attached to either side of the coupling, or either side of from the spool to the hub in alternate patterns of loading. This bolt is going through. There's a hole for the nut on this side, and the nut is drawn up, and I'm attaching the Shim pack to the spool side. The next bolt is just the opposite. I put it through there, the nut goes through the spool piece in an oversized hole, and now I'm attaching it on the other side. So every other bolt, it was attached the opposite way. So now if we have, it's a little softer system than just a rigid coupling. So every time I get some type of torque oscillation or thrusting or offset misalignment, it puts a shear into the Shim packs and allows the coupling to dissipate some of that energy. Okay, and they're sized for all kinds of different horsepower configurations, all kinds of different torques and speeds and so forth. Okay, So that's how this kind of works without getting into too much detail. This is a three-dimensional view of the compressor and the different conditions that we looked at. And this took a while to find. And it turned out to be really interesting, and it kind of made sense of what we were seeing in other animations. This is the unfiltered time waveform. So the shaft is spinning. We processed it so we can see rotation at 1 times RPM. There's very little motion in the compressor itself. We did detect a little bit of a soft foot in one of the feet, but besides that, it was pretty much rigid. This is the animation in the FFT, which doesn't show the rotation of the shaft. It just shows the rotation and what happens every revolution. So this is at 1 times RPM. Put my cursor on that and it'll show me how that motion works, like any good operating deflection shape. And if you look at this long enough, there's some thrusting in here. So most of the motion, there's a little radial or a twisting motion, but a lot of this is the axial motion, or this galloping in the shaft direction that I mentioned in the last animation. That's all good. It looks like something that I would say, yeah, we're dissipating the energy from residual imbalance, residual misalignment, your normal angular offset and radial offset. Where the thrust comes in is on the output side. So this compressor has a scroll that has six windings on it, effectively 6 blades. So you get a blade pass frequency at 6 times running speed. So if we put our cursor on that 6 times running speed around 21,000 CPM, this is the animation that we're getting. And it's mostly a twisting motion. We've lost all that 1 times RPM misalignment stuff, and we're now looking at basically torque pulsations from the compressor. And they're trying to twist the assembly there. So there will be some motion that we'll talk about in a minute that's really interesting that comes out of this. Go back down here. This is an unfiltered time waveform again, showing all the frequencies at once. We filtered out the 1 times and processed it. So the way this works is you take the time waveform, you FFT it, you filter the 1 times and inverse FFT it, and now you have a time waveform, but only one component, only one frequency in it, which is that 3580 RPM. Here you can still see that kind of galloping motion in the thrust direction of the shaft. The part we were a little more concerned about that might set off a torsional resonance was at 6 times RPM, blade pass frequency. And a little harder to see, but the galloping motion kind of goes away in this 6 times RPM filtered measurement. And it's kind of hard to see the twist. We had to find a different way to be able to look at the twist, but it did show us that, hey, there's 2 definitely different things going on here. And we need to look at least those 2 parameters. With everything has to be looked at turning speed of the shaft, and everything has to be looked at 6 times turning speed to make sure that this coupling isn't going off torsionally. And going off torsionally, what does that mean? This is something I got off the internet, just showing you what a torsional resonance does. You cannot measure a torsional resonance on the housings of your structure. It is the shaft, the rotating part of the shaft that's twisting and going into this resonant mode. And what happens in a resonant mode, as you get close to that torsional frequency, it takes off. And you can go back down the other side and try to avoid this speed range, but knowing where it is the big key here. Oh, I forgot to mention, our motor was a variable frequency drive, so we could set any speed that we wanted, and in the field it operates that way as well. So we stepped through it from 100% down to 45%, trying to look for this big point of high energy that would be shown in the torsional direction. Okay, so here's what we have. We took out that torque stand. We have 1 coupling now with the shim packs in there. And I'm showing the rotational speed of the shaft at 45% speed. It's 1611 RPM, and I filtered that out. So as I explained before a little bit, I took the total time waveform, just the raw data. I did an FFT of that so I could see the frequency content. I put a narrowband filter around the turning speed of the shaft, which this is, and did an inverse FFT. So now I have a time waveform that is just the turning speed of the shaft, okay? So I have something that I think how this should work. If I have an angle of twist in a soft system like this, I have the motor that's driving some of it, and it's exactly like this, very low amplitude on the motor side, and the torque that's reaction torque that's being generated will be a little bit higher on this spools into the spool piece. Same thing in the compressor, it'll be lower here and it'll react through that spool piece, and through the shim pack I should have something going on, actually maybe a twist in this a little bit more, and we'll see some that have a little more twist and others that don't. But this should be out of phase with the output side, and there should be some reaction response in the middle here. So one of the nice things about the MEscope software, you can put these lines in, you can select points you'd like data taken from, and just to see how this line of torsion basically on the side of the coupling is moving, I can judge the angle of twist and the magnitude of that torsional value. And that's what the little plots are at the bottom here. I have two different systems I'm looking at on this, or three different systems. This is the input side with the motor. So I'm comparing the phase of one waveform with the other. Okay, so I have two, here's my, there it is. I have 2 points of interest. I have the motion of this point and the motion of this point. I'm looking at the time waveform of each at 1 times RPM, which is at 1611. I'm looking for the phase shift, and that phase shift is 137 degrees. It's giving me an angle of twist that I'd have to calculate from that, but I have the values. I have the amplitudes of each of these, and I have the phase between them. So based on this, it's moving as I'd expect. And I believe if, at least in the field, when they had problems, there was a big sound coming, a buzzing sound coming out of the coupling. And physically, they cracked a bunch of the shim packs on the way. The output side is these 2 points I'm interested in, the phase between them and the amplitude. And they're almost in phase, and you know, not a whole lot of amplitude to them. The middle one, as I mentioned, the spool piece is doing most of the work, and I should see it flexing. In this case, it's pretty dead at 45 degrees or 45% speed, and we're about 55 degrees phase shift from one end to the other. So it looks like a low energy point. There might be a little torsion that's being generated, but not enough that's any problem for the coupling. This is a filtered response at 1 times RPM at 92% speed. Well, 92% is normal operating. They went up to about 108. So we went from minus 45% up to 108%. This 92% turned out to be right at 3,600, or roughly 3,600 for the motor. Now you're seeing what I tried to explain a little more action in the hub of the coupling, a little more action on either side as the torque's being transmitted across the shim packs. And this is what I believe is the normal response. So I did this at all these different speeds on a couple different couplings, and I kept getting very similar responses. So I'm assuming, you know, I've never seen a shim pack coupling operate before directly. I'm assuming this is how it operates all the time. If anybody in the crowd is a coupling expert, I'd take any type of thoughts you have on this, would be very interesting to me. So again, we can find the angle between the two. We can see what the magnitudes of this twist are to see if we're getting into a shear stress problem. And we can see if we've taken off. If we take enough speed steps in here, we should be able to see torsional resonance if it exists. This is 100%, so this is at 109 or 107% actually, 3,896 RPM, so just a higher frequency. And again, we did the same thing. So everything looks like a very similar pattern, slightly different amplitude changes and things like that, but nothing that's taking off on us. And I set, and these two didn't get it, but I tried to set all my graphs up at 0.015 inches. So 15 thousandths is a min-max type response. We thought a little more about the test stand, and we thought we better make another change, or else we might not be able to pick out what the problem was in the field. This is a field coupling, so it's a much smaller piece of equipment and has drastically different torque capabilities, but this is what they have in the field. So we took out the bigger coupling, we replaced it with this and ran through our whole series of tests again. And again, we're looking for this pattern. We're looking for this teeter-totter pattern on the spool piece. We're looking for an out of phase response on either side of that shim pack. And that's pretty much what we have. And we're looking for low amplitude. This is at 50%. And this was a pattern that started to take off a little bit. Amplitude was still very small, but this is what we're looking for. This is at 55%. This is at 60%. Get a little wave to it, but it's not teeter-totter anymore. This is at 65%. So we're working that spool piece a little more, nothing too detrimental. Again at 70, and 70 and 75 looked like they had a little more energy to them, but nothing, you know, that we'd really be alarmed at. 80%. There's 85. And 90 and 95. Okay, so not a whole big deal. This is at 3596, so basically turn the speed of the motor without variable frequency drive. This is above that at the 100% speed rate, which is actually 107. So we went all the way through the speed range, 45, all the way up to 107, and couldn't find any torsional resonance in that range. Our next thing was to do an actual torsional resonance test with a transducer and a modal hammer. And I wasn't able to be on site. They did collect some data with it, and I haven't processed it yet, but they had two modes that were well out of the operating speed range, but potentially could be excited by the blade pass frequency of the compressor. So we're still looking at that. This is, and then actually next week I'm going to do a grid style coupling in a plant. They wanted me to see what the alignment looked like on it. So I'll know more. It's a learning adventure. This is a scroll system in a sugar beet factory. And sugar beets are where most of the table sugar in the United States comes from. Everybody thinks of sugar cane all the time, but the big beet farmers in North Dakota and South Dakota are capture the entire market. These scrolls, they'll slice up the beets and boil them in water, and then they'll push them through these scrolls. And when they're saturated with water like that, they squeeze all the liquid out of the pulp, and it turns into pulp. And then they discard the pulp, and what's left is sugar water, and quite a bit of it. This is a very difficult analysis project because of the speeds involved. The output speeds of these scrolls are 1.2 RPM, so very slow. There's a massive gearbox on the input side of this scroll system that you can't see here. I'll show you the diagram in a moment, but it starts at 1800 RPM. Its belt drive is huge, and it drops the input speed to the gearbox to 216. And it's a quadruple reduction gearbox. And recently they were hearing a thump, and they were pretty worried about it because a couple of years ago, one of these big thumps turned into a fractured gear, and they took a whole gear out. So they're worried anytime they start their sugar beet campaign, which started about a month ago, until April. They're going nonstop, full bore. So they asked me to come in and look at the gearbox and see if I could see anything. Currently, they have one of my guys goes up and does it once a month and checks the gearbox, and he hears different things all the time, but this is something new that popped up. So we'll get to that. This is the gearbox, and my portion of this project was there's a little window on this side. It's about a 16 by 9 inch window, and another on that side. This gearbox input speed is 216, and there's dual outputs. So left and right scroll get independently run, or they're all geared together so that they run exactly the same speed. But this gearbox shows you where all the meshings are. Okay, so what I'm interested in, looking at the video through the side, what is the frequency that I'm seeing? And is that frequency of interest to me? And well, more about that in a minute. But here's our pinion. It goes through a 18 to 63 reduction. There's a 19 to 58, a 17 to 65, an 18 to 79, and we're out of this at 1.2 RPM. There's a few other frequencies that we'll be interested in. The gear mesh frequencies go from 3888 down to 95 RPM. So we'll take a look at those and some of the shaft speeds and whatever else we can pull out of this. This is a spectrum from the video camera. So we pulled out time waveforms for every location, every grid point that we define, thousands of time waveforms. But we also process those in FFT or Fourier spectrum so that we can pull out the frequency content. And in this case, you're seeing a whole string of the third gear mesh frequency. So first and second gear mesh are much higher frequencies, and they didn't show up. The third and fourth are the ones that showed up in the spectrum the most. They generated a lot of low frequency energy. So I have 1 through 10 times gear mesh frequency for the third mesh, and I have 1 through 8 for the fourth mesh. And you can see all the different possibilities we have in here. There's a lot more frequency content, but it's just like a transducer analysis, an accelerometer. Put it on your structure at the bearing. You're going to pick up whatever's transmitted to the bearing. When I shoot a video, I'm picking up the spectrum of every point in that video on the gear. So I'm seeing directly what the gear is doing instead of trying to figure out what the gear is doing as its energy runs through the whole system and out the bearings. Here's the locations of meshing that we're interested in. The third mesh and the fourth mesh are the two locations that we're going to be able to see through the ports on the side of the gearbox. There's another thing that you can do with the MEscope software that the competitors can't do. You can draw some lines on your system and see the motion and the difference in the motion. So I just outlined a couple of the gear teeth that are in view and put their links along here just to see how one mode relates to the other. And this is 1 times gear mesh frequency for the third mesh and 1 times gear mesh frequency for the fourth mesh. And it looks like the third mesh is flexing this gear. The third mesh is flexing something else back here. Okay, so even though you're doing a video analysis, you still have a frequency analysis and a time waveform analysis, especially for low-speed gear systems. That's really important. This is, out of the right side access port, a look at the gear. So this is 1 times gear mesh frequency. It's not the speed of the gear, the rotational speed, it's the meshing frequency. That's one of the biggest peaks that was on the previous spectrum. Draw your attention to the time waveform. If you have a cracked or broken tooth, you tend to have a big transient response in the gear every revolution. I could only take 8 seconds of data. It worked out fine for this. I could take almost a revolution of the gear, but on the other side, 1 RPM, I can't. It'd take me 60 seconds worth of data to be able to capture that. So the camera won't buffer that much, but I still can see what's going on. This is the gear mesh frequency, is what I'm seeing. All these, the periods of all these pulses is the fourth gear mesh frequency, I believe. Let me check that. Yeah, fourth gear mesh frequency is 95 CPM. A couple interesting things in here. You don't see this very often, kind of a slanted time waveform. That tells me that something's slipping, something's binding up and then releasing instantly. And what this probably is the tooth is bending. The tooth in mesh is bending as it loads up and then releases, and it moves drastically. So you get a little ping. So you're exciting the gear every tooth engagement, basically. And you get a real high response as it binds, and then it releases very quickly. And how that looks in the spectrum, or in the animation of the gears, the video animation, you can watch it and you can see these little kicks. So that's every tooth going into mesh. They bind on each other a little bit and then release. We're still not sure exactly if it's a gear problem or if it's a scroll problem. That scroll can also build up a bunch of pulp in there and bind itself a little bit. But this was the only one that did it. So they're really interested to make sure that they didn't have a gear problem. If they did, they could replace the gear now. And we're still on the edge of understanding all of this. What I propose to do is come back. They have 4 of these presses, and take time waveform, or basically video ODS on each one of them and compare them all. So they only have one that's knocking and making this funny sound. We'll see if the other ones are binding up as well. This is a same piece of animation, but the color contour on it, so you can see little color patches showing up and pinging different locations. So it's not the same thing occurring all at once. This is the time waveform, so you get all the frequency content. So they're exciting multiple modes constantly. This is my animations with my lines drawn on them, and with color contour and lines. So I want to see, is 1 times gear mesh frequency and 2 times and 3 mesh, are they doing the same thing, or are they all doing something completely different? It turns out they're all completely different. So there is different modes in the hub of the gear. There's different modes in the gear teeth, all kinds of different things that are occurring that make each one of these animations unique. And this is how I originally looked at it. Put some color contour on. These are a bunch of different gear mesh frequencies, multiples of gear mesh. And we have just a normal exposure at the bottom, so I can view the teeth and see them bouncing in there. And they seem to be waving a little bit. Nothing's quite the same. The color contours give you an idea, better idea of where the maximum motion is. So they're all different. every time you get a tooth engagement, it lets go, it rings the gear, and it rings all the natural frequencies. It's like hitting it with a modal hammer and getting the frequency response. But it gives you an idea of how it's reacting to this knocking sound or this binding of the gearbox or what have you. So when I go and look at the other 4 gearboxes, I can see if they're doing the same thing. And they're all supposed to be identical, but you know, you never know. This is another gearbox. This is in a cement plant. It's a ball mill or a finishing mill. What we have is a synchronous motor up here at 720 RPM, huge gearbox that has triple reduction, and we have a ball mill on the end. Oops, ball mill. Okay, this rotates. It has giant balls, steel balls in it, like shot put balls, and it rolls and tumbles those balls and crushes the rock into powder. And what you see all over the place, this is one of the dirtiest places on earth, is cement powder everywhere. And it can be, in some of the rooms, it could be 6 inches deep everywhere. Up on this platform, it was about 3 or 4 inches deep because nobody shoveled it off in a while. So not the most desirable place to be, but it was a very interesting gearbox. This is how it's laid out. There's a dual drive system after the pinion. So input is 720. It drives both of these 370 tooth gears. So now the speed of each of these gears is the same. That shaft mates up with the output shaft. And you're like, well, where's the bearing on this? There's A, B, C, and D are holding on to the intermediate shafts. Here's the pinion. It has a couple bearings in there holding it, and it's linked to the motor. Out here, there's only a sleeve guide bearing out on the output shaft. This shaft drops in and sits on these 36 tooth gears. So there's a lot of, not a lot, but occasional alignment issue that comes up because of the way this is put together. I asked a little bit about that, and this unit has been in operation since the 50s, and it's a very good design. And the people that originally designed it made it too good because you know, they expected them to wear out, and this thing just replacing parts every decade or so, and they've been running this thing, like I said, since the 50s. Okay, so we got 2 gear mesh frequencies. The one that really shows up in the data is the 3299, but the intermediate shaft speed, if you do any gear analysis, shows up as a sideband as well. And I did find one other thing, and I'll get to that in a moment. This is the frequency response. So this comes right out of the software that looks at all the pixels in the video. Its biggest response is the intermediate gear mesh, and it has something else going on here. Back up a minute, 172 and 36, neither of these is prime numbers. That's what you want to have. 47 teeth is a prime number, so every tooth on the 47 tooth shaft will touch every tooth on the 370 tooth shaft. If you have something like this, this has an assembly phase. There's 4 patterns of teeth that always come in contact. So the first tooth will mesh with the 4th, the 8th, and the 12th tooth. Okay, those are the only teeth that it will touch. The other will have just the opposite. So now we have 4 different patterns of teeth that are touching. This is called an assembly phase or a gear phase problem, and it's all tooth related. So if I run this thing and it sits on this 32 tooth or 36 tooth gear and the 170 mate, they'll run in patterns, and the wear pattern will be based on how many teeth or how many sets of teeth that'll come in contact. So I will only touch certain teeth on this gear and that gear, okay? If I go into maintenance cycle and you have to pull this rotor out for some reason, if you don't mark it, you can put it back in indexed improperly. So it could be one tooth off and it will touch teeth that it's never seen before. And what you normally get is a growling out of the gearbox that tells you, hey, you're chewing up gears. This one's a much lower speed shaft, so you don't hear it as much as there's a bit of a thump to it. But that's something that they were worried about. So the whole idea was to come in here and do some video, do some operating deflection shape as much as we could to see how the rotors are moving between bearings and get an idea of where this sound is coming from and what's causing it. One of the old maintenance reports said we have something at 26 degrees, that's 26 hertz that's undefined. And it turned out that it's the gear assembly phase factor. And it shows up a little differently. We have a phase factor of 4, so I should have 1, 2, 3, 4 pulses that look just like the gear mesh frequency. Instead, it's number 2 is the one that's showing up, and these are side bands of turning speed of the intermediate shafts. So it's like 95 RPM is what's showing up here. So this is 3,300 something for the gear mesh frequency. This is 95 RPM, which is the intermediate shaft, and the output shaft is 20 RPM. But that's what accounts for these series of pulses here in the middle. And this is 26 hertz in the middle of this little mountain of pulses. So that one problem was solved. Well, not solved, they still have the wear problems. So we'll have to see. But part of this analysis was, hey, let's look at the gears directly with the camera through one of the ports. They had a west port and an east port. This is the west side. It was the right direction that I wouldn't get all full of oil when I opened it up. So we just took data out of the west side port. You can see right away that the gear is moving. It's bouncing, and the teeth, are rippled, but it's moving. So we have a clockwise, if I'm on this side, we have a clockwise motion here and a counterclockwise of this mating gear coming in. And why this is a little more clear than this is because it's closer to the camera, okay? And you get a little shine from the lights that it's coming off of that. There was a mark on the shaft, and somebody made a note in the records at the cement plant. There it is, right there. There's 2 stripes, and they're on this side too, the mating edges. I believe there's probably some gear damage there, and it's showing up at gear mesh frequency because that's the engagement rate, and that's probably part of the problem. So I have my time waveform. This is filtered time waveform at gear mesh frequency. So I can see exactly what's going on as the gears move. This is the frequency response that we just saw on the other page. Put a little color contour on, and I can see, you have to look at this for a little while to see if it's moving because of the blinking that's going on, but here you can see it. You can see this slowly scrolling as it's bouncing. The bouncing here, it looks like we have a little out of phase behavior. So from this to the gear to that gear, they're moving at the same rate for some reason. And this one to that one, they're moving at the same rate. So they're flashing a little out of sync, which suggests that there's a little bit of an alignment issue in between the intermediate shaft and the output shaft. This is a vector plot. So I picked 8 different points along the teeth that'll be engaged. And as you rotate the shaft, there's a different amplitude response that goes through there, and you can see it a little better on the vector plot. So this has a little less energy, this has a little more, and again, that's a symptom that there's some type of misalignment between the intermediate and the output shaft. This is an orbit plot. Doesn't look like an orbit because the motion is so directional. But again, it gives you an idea of the magnitude difference between a couple of locations and gives you a little more to look at. This is motion that has exact numbers in it. So this is a frequency animation. The direction I'm interested in is the Y direction. So 8,000s, 6,000s, 13 1,000s on this side. So the highest is 13 thousandths. On this side, it's a little higher amplitude, 41, 36, 26, and 19 mils. So you have a little idea of what the total motion is. And then this is the last cut showing a little lighter version. I put a little contrast on there so that I could see the teeth a little bit better. And the hardest part a lot of times is trying to get enough light on something like this so you can actually see what you're looking at. And I had both panels up in front of that portal, and it was a little difficult, but you know, here we can see the color contour that's telling us where the biggest portions of motion are. And the last one, and I'm getting close to my ending time. This is a belt-driven fan, and this is my setup on one of the measurements I took. If you guys aren't familiar with this is a Kronos camera, and it's a color camera. They do also make a black and white, but they make the color that I use most of the time. This is some panel lights, and these are batteries on the back. I would suggest you get batteries, if battery-powered units if you can, because plugging stuff in with cables in a plant is very challenging. So we're going to take a look at this, and one of the things we're going to look at is the isolation system for this, and very interesting. And remember, I have turned the volume up and amplified these so that I can see the motion. Okay, and there's a reason why this whole thing, the whole floor, looks like it's bouncing up and down. And that reason is because the whole floor is bouncing up and down. This is a diamond grid plating, and I'll show you what that looks like a little better in another view. It's hard to see in this view with the dust on top of it. If this was in the sugar plant as well, there's sugar all over the floor. I put the color on so I could see the bounce. And the floor's bouncing, but the frame on the isolators is bouncing up and down. Okay, quite dramatically, as you can see from the amplitudes. This is the backside frame of the fan, similar as before. This is actually the same animation as before. I'm comparing it to the backside of the fan at 2269. So running speed of the motor, running speed of the fan. And I have two different motions. So the frame is being driven. It's a natural frequency in the structure. The isolators are really not doing their job. Here they're bouncing up and down in the first mode. Here's the pitching mode all the way across the beam from front to back on the floor. So you can see that we're working the isolators. I'm going to look at the other side. So this, oops, there we go. This is the same side of the fan, but from the other direction. Now you can see what I'm talking about these diamond plate. So these panels are on the floor. And I believe that they're just a loose connection. Underneath there, you know, these thin panels are attached to an I-beam that runs across the floor. So these bolts actually do go into the I-beam, but they're sitting on diamond plate. So they're not shimmed, they're just absorbing all that energy. So basically I have a loose condition underneath all my isolators, and they're bouncing up and down. And you can see that a little bit more on this second mode. I had a lot more motion right here. It looks like I'm working the isolator pretty hard. Here it's kind of a node point, and out there I can't see very much from this end. But this flexing is actually occurring. There's a lot of motion in this C channel that's supporting the whole frame. Oh, that was it. Thought I had one more slide, but that's okay. I'd welcome some questions if you guys had any, and Mark, if anybody's typed anything in, I'd be happy to discuss. Or if
Yeah, if you
you're,
have some questions, go
or if
ahead
you're
and
an
type your
expert,
questions.
tell me I'm all wet, and I'd be happy to hear your criticisms.
We did have one question in here. Can the camera be mounted on a moving vehicle looking at a specific part of the moving vehicle? Oh, absolutely. I don't see why not. You'd have to have a good mount.
Yeah,
You
you would
know,
have to,
some
you'd have
sort
to have a
of,
good mount, and actually um, they make mounts for that, like the motion picture industry, when they're having a camera, it's, I don't know what they call it, but it takes all the background motion out, and so the camera's steady. If you Google it, you'll find them all over on the internet, and I assume you could do that with it. Yeah, I haven't done it, but it would be interesting.
Next question. How sensitive is this method to camera motion? Can the motion of the camera be filtered out?
Yeah, there's a couple of things. One is avoided. And on this, I'm setting the camera up on this diamond plating, which is actually moving. In the software, you can pick a background location and subtract it from all the measurements. So if something in the background is bouncing up and down and it's an I-beam that isn't really moving, it's the camera moving, you can pick a point on that I-beam and say, subtract that amount of motion from every spectrum that I have, and it'll filter it all out. It's not a perfect process, but it helps quite a bit. The other thing is what you see here on the side of the camera is a little B and C port. This is a little trigger that turns the camera on and off. So initially, when I started doing this in November, I didn't even think of that. And I go touch the camera button with my chubby fingers and the whole tripod would move. And it would, if I took 8 seconds of data, it might take a second or so for that motion to dissipate. So I've ruined a good portion of that. Then I bought this trigger so that initially they let you turn the camera off with it, not on. Now the software is adjusted so you can turn it on or trigger on and off camera. But a lot of times the best thing is to avoid the vibration as much as you can, avoid the background noise.
We get a question, kind of a follow-up. It's to that question. Is asking negative average to eliminate camera motion, if that's an option.
Negative averaging.
Negative average to eliminate camera motion.
I don't know. Negative averaging is done in modal testing where the processor's running in the background. So you're actively taking data, and when you hit the structure with your hammer, it doesn't start when the hammer triggers it. It starts so many milliseconds before that. I don't know how that would be used to eliminate background noise. It's just a triggering event. Oh, maybe that's what you meant. Yes, you could. There is a pre-trigger. How is that? I've never used it. Now that I'm thinking about it, yeah, I wouldn't know how to set it up. It might be press the button and 2 seconds later it starts taking the data. I'm not sure. That's a good question.
All right, we can maybe try and get some
write that one
clarification
down.
on that one.
Yep.
Definitely. All right, here's a few more questions. How was your fan balance?
How's the fan balanced?
How was your fan maybe how was your fan balanced? I suppose he's asking.
Oh, this thing is a nightmare. It's really a bad setup, and it's the whole frame is flexing underneath the motor as well. So it's mostly a fan 2270 RPM problem, but it's flimsy. It's a bad design, I believe, that it is too flimsy for the application and the speeds that it's going. But to make any money on something like this, you got to cut corners, and I believe that's what they did with this fan.
Next question. This is related to the lighting. Who makes the who's the manufacturer of the lighting, the battery lighting is what he's asking.
Oh, it's called Generay. And some of the guys at Vibrant use a different light source. I originally got these. I think they're like 150 a panel, and then the batteries, you need 2 of them for each one, and they're about $75 each. So you're gonna double the cost with the batteries, but like I said, the having cables and stuff to power the lights is awful. And batteries work really well.
I think if you zoom in, you can actually see it on the back of that light right there. I don't know if you can.
I can do it.
Yeah, that's all right. You can't. There you go. Generay, G-E-N-A-R-A-Y.
And I think this model,
That looks good.
I can't see the model number, but this model, they've upgraded it. They don't sell this one anymore. They sell another one that has more LEDs in it, which is fine. You want as many LEDs as possible when you're doing this type of work.
Okay, we got a number of questions coming in here. This one a little more technical. Based on the coupling case study, can you relate the torsional frequencies with the MNFs to confirm torsional problems?
If I understand you correctly, yes. I think we've got it down to if we have a problem, we can detect it based on what we're doing. What you're looking at when you're we put those lines in on the side, this in the video, this is torsion that it's measuring. So you're measuring it directly. It's not lifting of the whole thing. It's the shaft spinning. In every revolution, it's telling you how much it's spinning up and down, if that makes sense. And knowing the difference between these two is the sine waves. So the angle of twist is there if we have the right magnitude. I don't know if I'm explaining it correctly, but I believe you have all the parameters there to see what your torsion is. The problem that we've been having is with the manufacturers of the coupling not giving us all the information as far as the inertia and the torsion testing that they've done and how it varies and things like that. But we're working on it.
All right, question about the camera. How long of a video can you record?
If you leave the camera, well, probably 2 hours or so. It depends on how you use it too. If you turn it off in between, when you're moving stuff around, that helps. And with the lights as well. The lights on battery packs, I've found that they last about 2.5 hours. And I know that because I left them on.
I think you might be asking how long of 8 seconds, 16 seconds is what I'm.
How long is the capture?
Yeah, that's what I'm guessing he's asking. Yeah. How long is...
Okay. Yeah, the capture is you can get a version of the camera that's 16 seconds. And I believe that's the highest they have right now. The one I have, the 2 that I have are 8-second cameras. But yeah, like the low speed event, like this 1.2 RPM output on the Gearbox, you'd never be able to get a full rotation. That would take 50, 60 seconds. But yeah.
Okay, let's see here. A question from Javier. He was a little bit late getting on the presentation. How could you see inside the reducer the gears movement when normally a reducer is a closed box?
There was a access port in the side. A panel about 9 inches by 16 on the Beet, Sugar Beet gearbox, and it was a round, I don't know, foot diameter portal in the cement plant gearbox. Yeah,
another question.
I mean, small gearboxes won't have access like this. This was 2 of a kind.
Let's see, let me jump down here. Can you review how you generated the reverse FFT?
Yeah. Let's see if I can do one. And this is probably something I should have done anyway. You go into the wizard, you can open up the raw waveform, and let me do one that'll be a little faster to process. Come on. Okay. We'll do this. This is just a motor, end of a motor. We're going to turn it sideways. We want to tell it how many frames the capture rate is. And I'm not going to take 8 seconds of data. I'm going to take 1 second. It shows me right here at 1,057 frames per second, which is pretty standard. All right. Sorry, this is taking so long. There. Okay, so I got 1 second of data. I'm going to set my distance, and known distance is about 6 inches, I think, right there. I can do a number of points, whatever I'd like, and extract the time waveforms. Go faster. Oh, this is coming off of a thumb drive, so it's, oh, shoot.
So while you're letting that, I was going to say, if you want, I can answer some other questions while you're letting that run.
Well, hold on. I'll just make it a little coarser.
Dial it back a bit.
Yeah, it's still going slow. Okay, yeah, what's your other questions?
Okay, well, there was a few other questions, camera related here. How long is the capture? What's the sample frequency? The highest frequency, what's the highest frequency that can be measured?
The sample frequency is 1,057 frames per second. That's at maximum resolution of the camera. So 1280 by 1040, something like that. You can make the camera go up to 40,000 frames per second if you want, but your resolution is going to be really awful. And the best resolution is that 1280 by 1040. So at that frame rate, the 1,057, and I've never changed it. That's what I take all my data at. Your F max, you have a Nyquist factor, so it's half of that. So 528 hertz, I believe, is your frequency range. And I was exploring a little of this. There is no anti-aliasing filter. So you can have aliasing problems that occur if you have a high input response that's above F max that might fold back into your data. And I thought that was happening on one of my jobs this week, and it turns out I couldn't figure it out, or I couldn't find it. So I don't think it was an aliasing problem, but that can come up. So your maximum frequency range of 528 hertz is pretty good for most applications I've been around. And again, the time waveform, if you put it in the Fourier spectrum, you have 528 hertz. If you use the time waveform directly, it'll give you, twice the resolution. Will be better as far as animation, but you can't pick out the individual frequencies. Now, what I'm doing here, it was a nice lead in. Here I have finished my thing. I'm going to replace my initial data with this data. And so I put it through the wizard. I get all the response I want. Here's my spectrum down at the bottom. So 3596, and you can see the motor bouncing on here. And they've had a problem with this unit. This should be 7200. So there might be a little camera flicker in there, but it looks like there's a natural frequency that's being excited at 2 times. So 36 RPM is 1 times RPM. Now, if I want to look at a rotating shaft at the same time, I can process the data, the time waveform data. Let me turn this off and filter out any frequency that I want. So here's my time waveform window. Up in the drop-down list is a transform window, and I can FFT it. So I'm going to turn it into a Fourier spectrum, so it's very much like this down here. And it's showing a couple of different things in the other direction. This is an overall level, but it looks a lot like that, right? There's a 1 times in there, and there's a 2 times, basically. Okay. In here, I'm going to put a dual cursor out. Let's say I want to look at that 2 times line frequency or the 2 times RPM pulse in there. I can put my band cursor around it. Let me get a little more. And effectively, I'm going to remove everything else in the spectrum except this peak. And this is whatever peak I want. I go back into the transform window, and I don't expect you to remember this, but that's what training classes are for. I can go into the window format function. I do a band pass and apply it. And now I have just that frequency showing up, right? It's still there. Everything else is gone. Now I can do an inverse FFT, and there's my waveform. Let me get one plot up. So here's my waveform. There's a little pulsation to it, so there might be a little bit of sideband energy or something in there that's showing up. Now, if I decide I want to look at just that 7200 or 7190, whatever it was, I can go in there and do that. And there it is. It's moving way too fast. So I take the speed down to 1 or so. And now you can see how the structure is moving. So some piping's moving. There's a big electrical box on the side here, and there's a big baffle box up at the top to take out the acoustic noise. So that's basically it. So basically you take your time waveform, you use this transform box, you do an FFT, you go and put your band around whatever peak you're interested in, and you do a window function with a bandpass window, and then you inverse FFT, and now you're left with something that's purely 7200, or in this, well, whatever frequency you chose. So you can play with that all you want. You can go back and redo it for different frequencies. This is called bandpass windowing, and I think it's better. I like the time waveform animation much better than the frequency animation, and we can see the difference. Yeah. Maybe it shows up in the movie a little bit better. But anytime you have a rotating shaft, you need to animate in the time window. If you can see the rotating shaft, or if you're looking at a coupling or a gear or something that's rotating, use this process and extract out whatever frequency you're interested in.
One of our engineers weighed in, Patrick, saying there was a command to do that from within the frequency window.
Yeah, I haven't used it yet.
Yeah,
I haven't used that
throw it out there.
That little hotkey yet. I'm still old school in it. Well, especially for something like this, you can't explain what it's doing by say hit the button. You know, those are the steps.
Right. We had one last question also. Given that given that flexible borescopes are available, can you plug one into the camera to get views that you normally can't? I don't think we've ever tried that.
Well, I assume the borescope has a light on it too, right?
I would guess, yeah.
So yeah, if that's the case, that's a great idea.
That is, as long as you can mount that, I don't know why you wouldn't be able to.
Yeah, it seems, yeah, the things you'd have to worry about is it moving around. You know, you get jostled, background noise, and sticking it into a rotating part. That's not real good. I've had stuff like that happen. Push it in too far and it takes it off or drags you in.
Dan, you want to talk a little bit about training?
Yeah, we got a class that we want to put on in November. And the more I thought about it, it's all these plants out there. It's an on-site class, so it wouldn't work for more than one company. But you know, if you want to schedule a class ahead of time, I'll come into your plant. We'll go through all the software. We'll go through all the camera stuff. We'll go through the theory, operating deflection shape theory, and then we'll have a project-based workbook where we're going to go out in your plant, take data on your machines, and process it. So you get on-the-job training, you get things you're familiar with. You know, there'll be some other canned things in there that you can use the data from, and it'll be a project-oriented class. And we'll all go in, we'll do it. We'll have a couple cameras available. We'll take our data and process our own data and understand what it's telling us. And you get all the tricks, and it's in a manual. It's a good class. It's something I've been wanting to do, and this coronavirus stuff, you can't hardly get in a plant where you're interacting with people. They like me because I can come in and I can be by myself, and I don't have to talk to anybody when I'm doing my camera work. But when I go and sit down in an office building, everything changes.
Good. And before we sign off here, I did want to go through some pricing real quick. If you are interested in ODS videos, we got two different pricings based on, if you're a current MEscope user, you can add on the ODS videos package for $9,000. If you're brand new to MEscope and you want to add ODS videos, you can purchase an entire package for $13,595. And we also do have, if you're interested in purchasing a camera through us, we've got two options for that. We've got the 1.4 Kronos high-speed color camera, the one that you're seeing here that Dan's been using. You can purchase that for $7,000, or you can get a higher res camera, which is the Kronos 2.1, and that's $8,500. And in any of these packages, if you reference ODS 10 when you give us a call or you talk to your MEscope reseller, we'll give you 10% off. So give you a little promotional code there to reference based on attending this webinar. So if you have further questions, you can always reach out to us at sales@vivetech.com, or you can reach out straight to Dan if you got questions about this webinar, or you want to schedule some training with Dan. You can reach him at modalguy@aol.com. With that, I think we'll wrap it up. Thank you, Dan, and I thank everybody for attending. Again, we'll get this, we'll get a recording out to you here in a day or so of the entire webinar, and we'll see you again next time. We'll get another webinar here spun up in a few weeks, so keep an eye out in your email inboxes.
If you have any suggestions for seminar topics, let me know. Mark tells me that a lot of people are interested in a top 10 type thing like I did before. If you haven't seen that, if you have any input, give me an email and let me know.
Absolutely. Good stuff. Thank you, everybody. We will talk soon, and take care.